morning, everyone. Today I'm going to talk about the real success story by deploying the machine learning model, how we successfully control improving our quality, especially for our case is storage data center. My name is Yongjin Choi. This work done together with my teammate Morat and then Chris Chang. So this is instead of using the reactive maintenance, we are using the predictive maintenance. So to give you some idea why is predictive maintenance is so critical, I'm just share the recent article. One of the articles says here, they are trying to the large language model training using the 16,000 GPU and then memory together. This training time is require about more than 50 days. During that training time, they got some interruption every 3 hours. That 6% more is caused by the hardware failure. So this is more than 1 billion system. So that means we can easily imagine that the interruption is waste a lot of money. So by predictive maintenance, we can predict and then replace the bad part in advance, then we can easily get the benefit, company-wise, also customer side. The other article says a CPU crash. This also happened in July this year, 2024. CPU is by somehow the improper voltage setting. So even if they update microcode, they cannot fix the problem. That means this CPU crash is gonna be also happening in the future. That means by properly we can focusing the defect parts. If we focusing that means business supply chain gonna be prepared for that. That also benefit for the company. That's why I'm just sharing these two articles showing how critical it is when we do the predictive maintenance, our business is keep working and then customer does not have any interruption. So to solve that problem, our approach is the dual machine learning model. The first model is to try to predict the imminent component failure. So in this case, the component, I'm just present the hard disk drive, SSD, also voltage regulator as an example. But we can also extend that. Whatever component reporting some sensor data, we can also try that to predict the failing in advance. So that's why my title says storage device quality control. Also using that, based on this first model, we can build a second model. Second model is focusing the long-term quantity prediction. So that means we can predict the number of the failing part in advance, and then that's gonna help the supply chain. They can have the part in stock very efficient way. So that's why my title says the supply chain management. So before I move on to the detail about our approach, I'm gonna starting with the more general idea, the general step, how a machine learning model is built. So this is a simple example how the classifier machine learning model is built. So that means this machine learning model output gonna be the classification label. In this simple example case is a fair and good label as an output. So in this model, we take the system information called the event log information. So the left side you can see that from the n number of customers, they are sending the event log information to our central location. So in this event log information, this is unstructured data set. Also, that means there is unrelated information included all together. So to meet our goal, the critical part, we need the filtering. What is the most relevant information from this two big size of the event log information? So that is called the feature selection. Feature selection, there's a bunch of different ways. So that's the very define the final performance of the model. So let's say by somehow we decide the feature, or call the sensor data from the event log information. With that information, as you know, though, we can separate that training data set and then test data set. Training data set is a builder model, and then test data set going to evaluate how our trained model is working well, or accuracy, or false positive way. So one of the feature selection is called causal inference. Causal inference is you can say which one is causing the output. So that is some simple way to describe that. So let's say, for example, we have this 5 time series is captured together. So each dot is each horizontal dot gonna be represent one time series. So this diagram showing that somehow we figure out the causal relationship. So that means, let's say our goal is to predict value at time t of the time series 0. So if we can figure out the causal relationship, that means the certain signal other than the time 0 is some delayed version is contribute the prediction value at time t. So with that information, causal relationship together, that means the prediction value at time t is not the unrealistic range of number. By using this limitation, some contribution, we can somehow reasonably set the range of the prediction value at time t. So a little more detail of the other aspect is also another important part is set the window size. How past the data set we're gonna including when we figure out this causal discovery. That is also ongoing research. So by properly window size time window W depends on that. Causal relationship may change that. So by sweeping the window size W, we may find somehow consistent causal relationship. Then that's gonna be the most likely give us the better outcome. So in this figure, let's say we set the window size W, then we are going to predict at time t plus t advance. What's the value of that? In here, we are set the time advance, t advance time. That means in other way we can call is the lead time. I can talk about lead time later in more detail. So with that lead time, we have some guarantee that we have enough time from the prediction, predict the target value y is enough time. We know that. So here, once we set the time window W, also from this multiple time series data, we also pick what is the which one is enough good information to predict the target value y. So that is the all related to the causal inference. So with that information, we can see that if it really working well, we can say the 30% feature selection. We can reduce that. Also, accuracy gonna be improved at 15%. So that's why causal inference is a quite efficient way, but also very challenging one to find the right signal. So let's go back to our approach. So storage system having a lot of the sensor data. They reporting that. So right now we just tracking millions the electronic device from the customer side. So using that sensor data is going to the service processor. We are using the call home program and then collect the sensor data. This is all unstructured data set. So from those central location, we are going to sanitize that and then make a structured database. That's the first step. We prepare the sensor data again first. So in this sensor data, this is a time series data, more like event-driven time series data. So this one includes all the environmental activity information together. That include the temperature, voltage, current, or others together. This one also includes the error value of the electronic device. For hard disk drive case, that include the read-write, correctable, uncorrectable error, and then read-write I/O counter per drive. Also, that provide the detailed diagnostic information about the other various error condition. Sensor data also include the network traffic by IOPS. This sensor data together, we're going to start processing them. So our example, one of the example is as a first model, is a prediction of HDD failure. This model is predict impending failure. Is it good or bad using the HDD sensor data. So model using the historical data, this as a supervised learning, as a both and fair and good information. So in our case, we use a machine learning model called extreme gradient boosting, XGBoost. This one is to build the ensemble of the decision tree. They build sequentially. And then each tree is trained to improve the error from the previous decision tree. The reason we are using the relatively simple model is to eventually we can deploy to the edge. That's why this is a good candidate for this application. So XGBoost also provides some feature selection approach. In this case, they list the feature important list as a rank. So we can also using this approach to select what is the good sensor data information. So just repeating what I've done says here, the workflow is we starting from the customer side storage, and then we collect the sensor data. Then with that unstructured data, we just by the processing, we make a structure, and then feature selection also process in that block. Then one part is going to generate the model, train the model. Then we can deploy that. So the model gonna be the label them. Is a failure going to happen or not? So once the failure is the impending failure happening detected, then we're gonna have the option. We're gonna sending the service engineer directly to the customer site, or we also let the customer know that, and then they're going to decide what kind of action they're going to do. So one of the ways to evaluate how the model is working well is called the ROC curve. So this is called the receiver operating characteristic. This curve is the plot by using the information, false positive and then true positive rate. So false positive means here, positive means here failure. So you can interpret false positive as a falsely detect as a fair. True positive means truly detected as a fair. So that means we can easily understand that how we want to reduce the falsely detect the fair. Only we're going to high number of the truly positive number. So ideal case is the plot, orange plot, if it's going close to the upper right corner, this is the best case, because that means interpret as the high true positive number and then small false positive number. But some cases it's not that easy, because we also consider other facts. I'm going to describe the lead time, the next slide. To consider lead time, we cannot only make the push to the left, upper left corner. I'm going to describe the next slide. So for example, this dot represents the true positive is 86% and the false positive is 3%. So yeah, now I'm talking about the very critical metric is lead time. Whenever you develop the machine learning model, this one should have enough lead time. What is the lead time? Lead time is the time at the moment when the machine learning model detects impending failure. From the moment all the way to the actual failure happen, that time duration is called the lead time. So as you can imagine, if we have the very short lead time, let's say 1 day or 1 hour lead time, that kind of model is we cannot deploy that. Because with that short lead time, we cannot do any action with that, even if we detect that. That's why this information is very critical for the real deployment. So that means describe other ways. From the issuing the service ticket to replace the drive, from that takes a few days at least for our case. So in this plot is showing the actual days, how many days span from we detect the failure, and then all the way to the sending the service engineer to the customer side to replace that. Majority of it gonna be at least for the 10 days. We need at least 10 days, or some case all the way to 25 days, some worst case. So vertical case shows the number of drive. So with this information, this one also depends on the application. So for this example case, they have the very relatively a few days or more than 10 days lead time, so majority of 10 days lead time to properly finish the job. So that's why we cannot have the high, only the considered high accurate model is not good enough. So our model is relatively showing the 5 months lead time. That's by sacrificing the accuracy. So this is this one showing the how our lead time distribution. So this is all the way to the 5 months is 5 months the bin size showing here. So that means many population is going to the lead time is all the way to the 5 months. So that means our model is showing the relatively long lead time, or we also adjust that to make that relatively long lead time. So by building this way, we have the enough action once we detect the drive is going to fail. That's how we learn the lesson when we actually deploy the model. We need to keep in mind we have enough lead time. So now I'm going to show you the actual deployment result. So this is a multi-year result. So in this plot, I'm showing that before and after we deploy the machine learning. So y-axis showing the storage outage happen due to this multiple drive failure. So horizontal showing each quarter, starting in 2008 all the way to right before we deployed the 2019 sometime. So before that, you can easily see that the outage is gonna be from that moment, we can see the drop about almost 2/3 of time. So this system outage is after deploying, we can see the big improvement there. That means that's gonna be avoid the customer work and then avoid the interruption. So the other actual example is for our case is during the COVID. Before and we deployed the machine learning model before COVID, but during the COVID, we cannot do any action. So we cannot send the service engineer to the customer side. So that means we did not. That's not our intention, but as that was for us is lucky to see that, to monitor that, without removing list going to fail, but we just sit there and then monitor that. How gonna be failure gonna be changing that? That's gonna be the plot I'm gonna show you here. So here you can see that the most left side, just due to the COVID, we just stopped pulling the drive. So before that we just deployed and then we just managing the failure rate relatively well. So y-axis showing the failure rate. Horizontal showing the every month time scale. So before that, there's the well-managed failure rate, but due to the COVID, we cannot send the service engineer to replace pull the failing drive, so by our prediction list. So we just continue monitoring what's the failure rate gonna be changed there. So like I described previous slide, our model is about the 5 months lead time. That means the most left side, we already removed the impending failure drive almost around 5 months. So that means you can imagine that, oh yeah, that's up to the 5 months, relatively we can control well the failure rate. So like you can see here, as we expected that, failure rate is consistently low around up to the 5 months. So after that, the failure rate is shooting up. So that is sort of the indirectly proving that our lead time is relatively okay, relatively consistent what the failure rate showing here. So right after shooting up, we have the back to the removing the drive again. So that means right away the failure rate is decreasing. So then eventually that's going to back to the original controlled failure rate. So that means this one also interpreted the other way. So this HDD case is some internal issues stay there. By applying the machine learning model, we just control that. But at some point, due to COVID, we cannot control, we cannot do any action. So that means we can see that still failure rate going higher. That means the still issue is stay there. So then we, by action again, removing the drive again, then we just controlling that. This is the where represent our example machine learning model is working well in the real field. Then I'm going to talk about the second machine learning model using the developed from the first one. This one is the estimate the quantity. So that means we're gonna prepare the saying the guarantee the procurement time. So that is the acquire new part quarterly based. So supply chain want to know that what's the quarterly based new part they have to prepare. That's why we have to estimate that what's the amount of quantity. So let them know that they make in stock. So using the this plot showing using the XGBoost model, you can see that this plot saying the what is the from the failure prediction from the most left side, but still unfailed one. It's not failing one even if we predict that. That's the remaining one is showing here. So that means all the way to the right end, still around the 25% is drive is not failed, even if we predict that. That means you can logically think about that's gonna be eventually fail the next and next quarter. So by using that logic, our focusing for the quarterly estimation is by the summing all the beginning of the quarter, we just predict that. Also, we also summing that with the previous quarterly previous forecasting. This is smoothly decreasing. We can expect that this number unfailed one all the way to the going to the current quarter. Also, we also another one is a 2 quarter before. That also still residual remaining unfailed one there. So by summing all three together and then by scaling some factor, then we can properly forecasting how many part going to fail in the current quarter. So by doing that, we can reduce the risk of the supply chain shortage. Our result looks like 95% better accuracy here. This is our second model is working for the focusing the quantity. Also, this same approach going to be applied to the SSD failure prediction. So compared to the HDD, SSD also require different set of sensor data. So that means we're gonna using the different feature. So that also very challenging part. Once you select a different feature set, and then we have to build a separate model for the SSD. So our early deployment success is here. So before we deploying the certain customer side, they have the reporting more than 80 failure happen. But after we proactively removing that, only 4 is going to be failure. So that is our first model for the SSD. By the similar way, we can also forecasting how many parts quarterly we need that. That approach also showing the 98% accuracy. So this is still ongoing. We continue improving our model. This is a application approach what we've done for the HDD. Also, we can apply to the SSD also. The other one is the voltage regulator. So we also apply the same way. We're gonna build the imminent model, failure model that is using the only I/O activity information that give us the less than 10 days lead time. I'm talking about the right side plot. And then this gonna be the detect imminent system failure. Also, long-term forecasting. We also include other feature, such as voltage, temperature, current, power, I/O activity altogether. We can also long lead time, more than 6 months lead time, prediction model before the system failure happen. So that means our two model approach also apply to this voltage regulator. So that improved our quality. So to summarize my presentation, so I present the two models. One is the imminent failure model that can apply the other storage components. So once we have the related sensor data information, we also do the quarterly failure prediction based on the first model, including the other sensor data together. So that means gonna be that help the supply chain managing. Also, while we developing the model, there is a couple of things we think is emphasize that. Definitely the historical sensor data, we have to enough to save them for the properly training. Also, critical part is selection. Which sensor data is most critical? I described the causal inference as one example. So depends on how efficient is that selected feature sensor data. That's gonna be the define and then limit the performance of the machine learning model. So, and then also most critical part is lead time. If we do not consider lead time, how from the moment the model is detect the failure and then all the way to the actual failure happen, if that lead time is not long enough, but long is depends on your application. If it's not long enough, we cannot use the model. That means in real application, lead time is the most critical part. So that means if you want, but that means higher accuracy going to the shorter lead time. But if you want to make a longer lead time, that gonna be make the accuracy getting lower. Accuracy getting worse. So when you develop the model, you have to trade off between these two metrics. You want to sacrifice the accuracy and then still keep the longer lead time, or sacrifice lead time and then shorter lead time and then higher accuracy. That is the trade-off. We have to keep in mind that. So, but they cannot. I think we cannot avoid that. So we have to make a decision based on what kind of application you guys are working on. So this is a lesson I've learned, and then I share you guys. So this is the end of my slide. So let me give you guys time to Q&A. Yes, sir.
Are you pulling the parametric data from the systems or from individual storage devices, HDDs? Okay, I think you had a short list that was like uncorrectable errors, these kinds of things. Are these system level, or are you pulling like individual drive parametric data?
Yeah, the question is the data is coming from the device itself or system info from the system. Is that kind of a question, right?
Yeah.
So I think this is a mixed in this event log. Some data transparent all the way from the device component, so directly reporting to the system. Also, some other event log information is the received sensor data, and the system is some counting that. Then they are reporting that. So two kind of information are mixed together in this application.
Are you planning on adding any other? I know there's some additional telemetry things going on in OCP, for example. Are you planning to add more of that parametric data to the model, or do you feel like you found the parameters that give you the most accurate model?
So question is, I'm going to plan to add more telemetry data, right? So yeah, we want to continue working on that. So we are not thinking the whatever the sensor data we found out is the optimal. We don't. Yeah, we keep searching for that. So what other information we are missing? So some information is also adding the improving the model. That's what we continue working on. So we are not saying this is a feature for this model, but we continue update that. We continue looking for the other sensor data. So try to include together. Yes, sir.
So I was trying to wonder, paralleling that thought process, is all this built into the firmware of the array, or is all like is your model built on the array sending data back to a central database at your company, and then the model runs there and says, oh, you better go do this at company X?
Yeah. Yeah. So question is, my model is all the way to the edge array or on a central location. So that is a question, I guess.
Yes.
So yeah, right now is our implementation is a central location. So that means the customer data sensor data is collected to the central storage. Then we process that, and then depends on the model decision, we just respond what's the proper action. But right now is we are working on the how to deploy that directly to the edge. So that means the array, right? So by doing that, we're gonna reduce the bunch of the traffic going on. So we're gonna reduce that, definitely this benefit. Also, we don't really too much worry about the lead time. So once the deploy to edge, we can react very quickly. That's the benefit, and then that's our goal right now. Yeah. Yes.
How do you put the lead time constraint in your training? Do you train for a 6-month prediction, for a 5-month prediction, 3-month prediction, whatever?
Yeah. The question is how we set the lead time, 3 months, 6 months, 5 months. So that is like I mentioned, that is sacrificing the accuracy, sacrificing the false positive rate. So that means we're gonna change the threshold value. So threshold value means some probability. So what's gonna be the fail probability? By relaxing that, we can inevitably we can include more false positive. But with that risk together, but still relatively we can increase the lead time. But that is also we consider other ways how to not sacrificing other factor and then improve fully control the lead time. That is the also we are working on right now. Yes, sir.
How often are you pulling the customer data to do the inference?
Yeah. Question is, you mean how many times we are pulling the
The frequency.
frequency? Yeah, frequency. So question is the frequency of the pulling the customer data. So it depends on the different sensor data. Some sensor data information is every a few hours. Some critical sensor data is even a few minutes. So we just giving some priority. Which sensor data critical? We just more closely monitor, or a few hours is good enough, or every day is enough. Yeah, there is a different kind of list there. Yes.
Curious to understand how do you improve the model performance of the
Model. Sorry. Can you? How we improve the model performance? So in this case, model performance is the one obvious thing is we're gonna select adding the different feature set. So it depends on which feature that we're gonna include that. That also overall improve our model. Also, we can also using the different machine learning approach, but because we are considering the deploying eventually to the edge, we are not trying to the more fancy deep learning model. We are not consider that kind of model because we have to focusing on the edge application. That's what we are working on. Yeah.
How are HDD and SSD companies, how receptive are they to this? I mean, you basically go to RMA a drive that you say, we believe this drive will fail, and you have some false positive rate as well, right? I mean, does the HDD company say, yes, we believe your model, and we will ship you a new drive? Or how do you convince the device vendors that your data is accurate? I guess this kind of same data that you shared today, or fairly receptive to that?
Yeah, let me guess your question. So you are trying to say how we convince our device vendor our failure rate is relatively acceptable, right?
Correct, yeah.
So I think one part of sensor data is directly coming from the device vendor sensor information. Also, the other part also, because the connection from the device all the way to the system, there is also some component there, also some trace there that other components together, they couple together, make also create the error. So we are not saying the device is only create this failure. We also combine with the all system is running together. That also creates the additional error together. So also device vendor is they may not have a chance to experiment like we are doing, because in this case we are collecting the actual customer running system. So device vendor maybe mimic that traffic, but this one is a multi-year data collection. So from the real application running from the customer side. So that means we may have the different conclusion, but each conclusion I think correct, because it depends on what kind of data they are looking at. Definitely they're gonna have the different conclusion. Yeah, that's what I'm thinking.
Let's think about this way. The reason why we deploy a program is we have one feature that the vendor already knows, right? We don't scope out there and select drive, right? We see that failure rate. The vendor is already at our mercy to get help to come fix it. Therefore, our drive or whatever is working. So the empirical data are already there. We're just trying to help them by not holding them liable for all.
Thank you.
Yes.
When you do detect a failure, are you pulling an entire system, or are you pulling individual units, individual devices that have particular problems?
Yeah, the question is when you have to detect the failing component, are we removing the whole system or some component itself? I guess that's the question. So we try to definitely we are trying not to interrupt the customer system running. We try to avoid that for interruption. So even if we have the one drive fail, we detect that. We are not trying to remove that because this is a RAID system. Until the multiple drive is a failure same time or very short period of time, then that moment we can remove the one of the drive. So try to minimize customer interruption. So we just wait until the multiple drive failure happen. Only that point we try to sending the engineer and then remove that. That's what we are doing currently right now. Yes, sir.
How accurate is self-test results in respect to this model? You mean the self-test results that are supported by the drive vendors is not accurate enough to determine the drive failure?
I guess the question is how accurate our model.
But the drive self-test, the drive vendors already support something called drive self-test results, right? It determines whether the drive is in a healthy condition or not. So how accurate are those self-test results as compared to your model? Predicting the failure to your model compared to drive self-test reported by the drive vendor?
Drive vendor. So are you saying probably similar question? You're saying the drive vendor reported the failure versus our model, using our model is a failure, right? So how?
So you mean to say the drive vendor's reporting of drive self-test result is not accurate enough that we need to rely upon these models?
So yeah, I think the question is drive vendor reported a failure versus our model is reported a failure. So how accurate between them? So I guess, right?
Yeah.
So I think probably a similar answer. I'm going to say that drive vendor is the different condition. They may not using the same application running or same system. So they have the different condition running. So sort of the state they gonna reporting some error, but our system also different stress going on by using the customer application running. So that's why we collect the customer running system data set and then we analyze that. So based on that data set, we are saying the little bit different failure happening, but that does not. We are saying the vendor parties some parties problem from by vendor, but some parties by our system running all those stress together, that causing the different failure happen. So increased failure happen in this case.
Which one to believe?
Hmm?
The drive vendor says it's good and you say it's bad.
It's really a catastrophic failure to the site, right? So these are not software failures, these are actual drive failures. Multiple error that pick up these events and these events on some. The customer will not also able to develop that. So
Yeah, I think we have time is off. Yeah. Yeah, thank you for attending. Thank you.